Okay, Jane, here we go. Here's your problem. I'm going to go to Desmos to show you how I think I proved to myself that I did the problem correctly. I've set variables A is 1.1, although I can change it with a slider, and little a. It's 1.2, although I can change it, and K I used instead of the letter R because Desmos treats R as something special. I've defined f of x as 1 over k squared plus x squared to the 3/2 power, and I've defined g of t as, here's your problem, a times k times the definite integral from a to t, which we're going to be infinity, of this f of x definition. And now if I take g of 10,000, for example, and that would be like the definite integral from a to 10,000 of f of x dx, and I get this 0.77009. And here's the answer that I came up with. A over k, which is in our problem would be a over r, times the quantity 1 minus a over the square root of k squared plus a squared. And you can see they're the same. And if I add another 0 here, or they're close to being the same, if I add another 0 here, getting closer and closer to infinity, you can see that these are getting closer and closer. I'll put another 0, and boy, they're really close. One more 0. Well, now they're a little different. Okay. But, so the question is, how did I come up with this answer? All right. I'm going to see if I can copy this onto, no, I can't. Okay. So anyway, we'll go to board 2, and I'll copy down the original problem. We're told that u is equal to a times r, the definite integral from a to infinity of dx over the quantity r squared plus x squared to the 3/2 power. And we're told to use x equals r tangent theta. Now, how you would know to do that without that hint would probably require you to have read a chapter or done some problems dealing with trigonometric substitutions and recognizing that that might work in this case. And since we're have an upper limit of infinity, hopefully you've had some material about finding definite integrals where the limits are include at least one where one of the limits is infinity. Usually we say the limit as t approaches infinity of a to t, and then this thing right here, I'll just call it f of x dx. Okay, so that's how you, hopefully you have had some material on that. But let's do the substitution and see what happens. So this will equal, well, let's first make the observation that I've got an x squared here. So if x equals r tangent theta, x squared equals r squared tangent squared. And we'll also make the observation that if I take the derivative of this expression, then dx will equal r secant squared theta. Again, r is a constant. The only variable is this little x here. So now, using this information, I'm going to see what happens. And I'm going to leave off these limits of integration for now. We're just going to find an antiderivative. So a times r, indefinite integral, dx is r secant squared, oh, I should say secant squared theta d theta. And down here I've got r squared. X squared is r squared tangent squared. To the 3/2 power. Now I'm just going to continue working on this portion. We'll add the AR back in later. So I've got r secant squared theta d theta, and the denominator inside the parentheses I can factor out the x squared, and I'll get 1 plus tangent squared. This whole thing still to the 3/2 power. And then the whole key is that 1 plus tangent squared is secant squared. So r secant squared theta d theta over, I'm going to picture replacing 1 plus tangent squared with secant squared, but then I'm going to raise each of these factors to the 3/2 power. So r squared to the 3/2 power is r cubed, and secant squared to the 3/2 power is secant cubed. And I'll put this AR back in. And let's start working to the right and see what happens. Okay, so I can see that, well, I've got r squared, 1 over r squared, which if I move it out front, I'll have AR over r squared, so I'll just get A over r out front. And secant squared over secant cubed is 1 over secant, which is equal to A over r times the indefinite integral of cosine of theta d theta, which finally is equal to A over r times the sine of theta plus c. Okay, so this expression right here is an antiderivative of this mess. And what we would like to do so that we get the proper limits of integration is replace theta in terms of x. So we've got to go back to this guy and solve for theta. So if I solve for theta, I get x over r equals tangent of theta. So theta equals inverse tangent of x over r. So now we're down to this. I want to find the, so let me put the, rewrite this with theta replaced by the inverse tangent of x over r. So I've got A over r times the sine of the tangent, the angle that has a tangent of x over r. Well, is there any way to, what is the sine of an angle that has a tangent of x over r? Well, I'm going to draw a little right triangle. Here's theta. It's an angle that has a tangent x over r. So the hypotenuse is the square root of r squared plus x squared. So the sine of that angle is x over the square root of r squared plus x squared. So I can replace this, I meant to go to blue, with x over the square root of r squared plus x squared. So I'm going to jot that down. I've got a over r times x over the square root of r squared plus x squared. Okay, so let's go to the next board. A over r times x over the square root of r squared plus x squared. That's the antiderivative. And we're trying to take the limit of this as t approaches infinity from a to t. So we're still taking the limit as t approaches infinity of, I could put the a over r out front since it's a constant. I'll do that. I'll make it a capital R. So this is what remains. Put the a over r out front. Put t in for x. Minus, put a in for x. And now the question is, as t approaches infinity, what happens to this term right here? Well, I could write this as t over the square root of r squared plus t squared. And if I multiply numerator and denominator by 1 over t, the numerator becomes 1, and I can introduce this t into the radical by squaring it. So I can say the square root of r squared plus t squared over t squared. Because if I take the square root of the t squared, I'll get 1 over t on the outside. And now I can rewrite that as 1 over the square root of r squared over t squared plus t squared over t squared, which is just 1. So I've got 1 over the square root of r squared over t squared plus 1. And now what happens to this thing? What is the limit as t approaches infinity? By the way, I'm not being very precise in showing you this work. If you have to, you don't have to show your work. But as t approaches infinity, this term approaches 0. So I just get 1 over the square root of 1, which is just 1. So the limit of this thing in brackets as t approaches infinity is, we got the a over r out front times this circled term in red has a limit of 1 minus a over the square root of r squared plus a squared. Now you might want to substitute that into your answer or your online site and see if you get a correct solution. Let me know if you don't, but I'm pretty sure that should be the guy. based on what's happened here. As A changes in value, big A, little a, R, they're still very close. Okay, so I think that this expression is the answer with K replaced with a little r. Okay, so I'm going to end the video, post it on YouTube.